there is a difference there. Applications of indefinite integrals, or antiderivatives, we already have seen. You've seen it in calculus 1, and that is simply if you talk about velocity as a function of time, its antiderivative will be the location. Okay, so that's the whole application is so big that it deserves a separate class. Here we're looking at just about everything else, all other applications of integrals that are not involve motion. Okay, so and that is some of these are geometric in nature, such as this. We're talking about areas, but we'll also be talking about surface. Not only about areas of flat regions, but also flat regions that are not regions of surfaces, areas of surfaces, as well as volumes and everything beyond that. That's how it's done. If we once again take a look at this, what we did yesterday, so I have two functions. They can be looked at separately, f and g. F is the purple, the orange one, and f is the blue one. Both of them are plotted with the Excel in such a way that, Excel can actually draw a curve. Okay, no problem. So, but I intentionally plotted these as with a bar. So it's a bar chart. Okay, both of them are. Okay, why? Because they point out that the purpose of this plotting, which is Riemann sums. So these are Riemann sums. Areas under the graphs. It just happens to be still a step function. So we're sampling our functions a little bit, and then the hope is that we're going to figure out what's going on, and then we'll take those limits to produce integrals. Okay, but at this point, as I tried to explain yesterday, is even though the main application is the way to visualize it is with the areas, and you can see the overlap, and but remember, so we still can go back to motion and to explain why is the area negative, in what sense could an area be possibly negative, and that's the explanation. If we speak of displacements, displacements could be positive or negative depending on the direction of your motion. Okay, so and that's what integral is, the displacement. So then if two people are moving, or two cars moving in the opposite directions, then we add the velocity are being added on one hand. On the other hand, you can simply and then the question is, well, what happens to the how much has the distance between them changed, and that you will need to integrate either velocities separately and then find the two displacement and subtract, which is what this is, or you start over. You start with the velocity of how fast they are moving away from each other, and then integrate that. Okay, so these two things are fairly straightforward, especially when the speeds are constant. But the interpretations are still more visual, I think, when we deal with areas. So just let me make a picture that is slightly easier to follow here. So like this. So we have I have one function. Okay, so I have one function. The orange one looks like I don't have orange. Okay, so purple. I don't have orange. Here's orange. Great. Orange. It is some kind of parabola. The other parabola like this. Okay. So that's my G. Okay. So and then the other one is blue. That is a parabola that points up. Okay. So two graphs. Now nothing more than that. That's all there is at this point. And then we proceed on. We can with areas. Let me plot the areas that we approximate. So I will do it separately. So so there's the x-axis here somewhere. The x-axis right here, where the y-axis doesn't matter. But this is the area under the graph of f, roughly. So like this, and I could even plot these lines to indicate the Riemann sums. So this could be the area under the graph. Okay, and then like this maybe, and then the area under the graph of the other one is this. Is this. Okay. So I'm doing pretty much the same as what was done by Excel, just doing it by hand. And then the areas are subtracted. So that what you look on the right over there, it is the two Riemann sums are being subtracted from each other. Once again, the interpretation of each of them is an approximation of that area under the graph. So you have a continuous curve. The region is curved, but you approximate with those bars, and they sum together, give you a Riemann sum. You subtract them, and you get the difference, and then you just interpret that difference if necessary. We interpret it as a displacement between two cars. So this is one velocity. This is the other velocity, and if they are moving in the opposite direction, then you will subtract them. That's the explanation of the different sign. Okay, so that's pretty much the whole story. You can let me make a picture that looks easier to understand because there is no overlap. Well, let's make F and G not overlap. So one is strictly above the other. So I'll have my F looking like this, and I have my G looking like this. Well, in fact, yeah, that's fine. At this point, it doesn't even matter. It doesn't even matter where the x-axis lies. It could be higher, below. It won't matter whatsoever. I have my limits, say A and B. So once again, this is F, this is G. Once again, I could mark the area one and the other, and they will. This time, there won't be any doubt about the meaning of the difference between those two areas. So let me mark it anyway. So I have my blue one. Let me just make them stand far apart. So this is the area under the graph of F, known as the integral, also known as the Riemann sum, approximated by it. And the other one is this. Okay, then there is no doubt of what that difference we're looking at the top represents. It represents the area that is marked with blue but not orange. The end. So, and it is a positive area. So this one, positive area. Okay. So and that's pretty much all there is as far as we are concerned. Our interest is remember. Well, I made that point yesterday, but may have been forgotten. The point being, how do you compute the areas of regions that are not represented by a region under the graph of a single function? Okay, so when we did a half of the circle, that was, we had an explicit equation right there, and that was sufficient. In general, if we face a picture like one on the right, we need two better methods, and one method is to represent it, the curve below and above with two curves, which gives you so much more flexibility. So look at this. If we look at that picture on the right again, the region. Let me mark it. This is the region. Okay, so the question could be, to begin with, suppose we are facing that computing the area of that yellow region, and we cannot compute it in the same way as before with a single integral. Okay, so turns out that, but that's okay as long as we can represent it in the can represent the upper edge with one function, lower edge with the other. All we have to do is just to subtract, which also. So let me try to say what write what I wrote there. So the yellow is blue minus orange. Okay, right here. So the yellow area we're interested in, it will be the blue area minus the orange area. Okay. Or if I know algebra, then what you're going to have is what is it? Yellow plus orange is equal to blue. Okay, you see it? right? So I wonder if you can think of a name for this property. Area, area, area. So we talked about a similar property not a long time ago. Property of areas. Additivity, right? So additivity, we were talking about a similar property, but in a very different additivity of areas. It was just arranged in a quite a bit different way. So let me just once again refresh your memory. I could have the same thing like this, and yellow. Let me pick the yellow one. Okay, so this is the yellow. Plus, no, that's not the yellow. This is the yellow. Okay, and the first one is the orange one. Okay, so the yellow. This is the yellow. Okay, the yellow plus the orange, right? Plus the orange is equal to blue. Okay, so like this maybe. Okay, once again, yellow plus orange is equal to the blue. That is the additivity property we talked about last week. But it is, as you can see, even though the property is the same, so two pieces of two regions align together, form a new region. What happens to the areas? You add them together, as long as there is no overlap. Okay, so that's when the two regions are aligned to added to each other, combined with each other like this, or they're combined like we have over there. But it's the same story. When areas are combined together in a new region, when the regions are combined in a new region, they are areas added together unless there is an overlap. Okay, so once again, we can say that their overlap is so thin that that curve over there in the middle, the graph of G, is in fact the only overlap of those two regions, one yellow, one orange. So then when you add those two regions together, you end up with a region of the whole thing, the area of the region of the whole thing. Okay, so that's the additivity property. It just has a different idea, and we want to express it in a. The idea is very simple, and so unfortunately, that simple idea sometimes is lost when you turn it into these, give it the form of an integral. Okay, but well, we have to do it because that's the way to compute it. Just remember that's what we're after. So we're gonna express. We have three areas. Two of them are just integrals, just like those two on the left, as well as those two on the right. One is a region under the graph of F, the other under the graph of G. So those are two integrals, so we write them as integrals, and then we'll see just what happens. But we already see that pretty much here. So these are the two regions. And they combined together give me, where's my, well, I don't have it here, but the area is equal to the difference of these, and we just represent this as two integrals. So let me just start over, just looking at the picture which is on the right, and write what we see in terms of integrals that we learned in Calculus 1. So, okay, the yellow area is the region under the graph of F. Now let me, I think I'll take this one. I think I prefer this one, which is more to the point. So, okay, so let me write it out. So the area between graphs of y equal f of x and y equal g of x, that's the yellow one, right? What is it equal to? It is equal to the difference of those two other regions, and I'll write them separately as integrals. Okay, so the blue region, what is the blue region? Look at the picture. What's the area of the blue region? Not F, but what? What about F? F gives you the graph of the top. The area is given by the integral, right? So integral from a to b, fx dx. Okay, subtract. Now, same story. I'm looking at now, subtract the orange. on the right, so it's graph under G, so it will be the integral of G. Okay, so to subtract integral gx dx from A to B. Okay, so we base this on our understanding of Riemann sums, as well as understanding of what? Of areas, how they combine together, and they have to satisfy this additivity property. Okay, so based on this is the conclusion that we make, and we in fact can, that's the way we did it. That's exactly how I computed the area of the area, well, not this one, but rather this one. Just a minute. Okay, so this is how I computed the area of the circle. I took F and G and just computed, I computed two areas and then added them together. Okay, so okay, there is however, we don't have to stop here. We can improve this result if we remember certain property of integrals. What is it equal to? The limits are the same, the limits of integration A and B. So what can we do with these two, with this difference of two integrals?
Can you just write one integral symbol?
Yeah.
And fx dx minus...
No dx, no dx. It will be the difference of two functions. Right? Fx minus gx, that's all. This is hardly obvious. It is just supposed to be familiar, that's all. So what is it called? Two integrals turn into one.
Sum rule.
Sum rule, that's right. You can say difference rule, but I think just as well. The sum rule. So in the difference, you usually have a plus sign there, but it doesn't matter. So that comes from calculus 1, some of the basic properties of the definite integral. The basic property is the sum rule. So, and it is like, so do you remember how you justify the sum rule? So think about it, well, think about this picture. So we know that the integral, this integral over here, we know what it is, right? It is the area between the two graphs. It's the yellow area, right? And then initially we understood it as the difference of the other two areas. That's fine, blue minus orange. But we're claiming something entirely different. We're claiming the one integral under the graph of a new function. We had function f, function g. Okay. Right here, and that worked out fine, but then turns out that we produced a new function, f minus g, and why does it work? Why is it the same thing? Well, the explanation might be it's like, in case you don't remember, it is like you start with your Riemann sums, and then you rearrange them. Let me try again. Let me try, I don't know if it works. Okay, so suppose these are the bars of the Riemann sums. So the upper edge is f. This is f. The lower edge is g. Okay, so well, let me make a few more like this maybe. Okay, so now what if I take all of these rectangles? Let's see if I can do it. If I take all of these rectangles, what happens to these rectangles when I do the subtraction? Where's the thing? Here it is. Maybe it works. That probably won't work. Okay, so what I'm trying to say here is, what if I take these bars and move them? What? Imagine I'm holding a bunch of pins. I have one, but imagine I have a bunch of them, okay? And they are like this. And they are not aligned in any way. Okay, so the upper edge is given by F, the lower edge is given by G, and then what I do is I drop them like this. And so that they align at the bottom. So I drop them on the x-axis. Okay, so just like I have it over there, if I have a bunch of lines, Well, let me make a few like this. And so they're misaligned, and once again the y misaligned because the upper is given by one function, the lower is given by the other function. But that if I want to reduce to one function, then what's going to happen is I'm going to drop them. The bottom will be aligned with the x-axis. So I take the x-axis and drop of these pencils of those bars on the x-axis, so that the bottom is at the same height. So for example, like green one. And the red one will go up, way higher. The blue one is slightly higher, and then this one is almost the same, and the black one is higher. Okay, so once again, this is F, this is G, and this is F minus G. Okay, so the area becomes the area is the same. We just rearrange the material that is contained between two graphs. Rearrange them in such a way that the bottom becomes flat. The bottom end of those bars becomes flat. So either you think about pencils being dropped, or you think there is what maybe sand is held between two things, and then what do? You drop the bottom and see what happens. And then it's the same area, turns out, and then the last area is much easier to deal with. Well, because there will be only one integration. So, for example, so I'm going to use this so by the sum, or what I meant to say here. If I use this formula now, I could solve problems such as once again, let's review that example of the circle. I'm not going to go all the way, but I'm just point out that this is f of x. Graph of f of x is 1 minus x squared. This is graph of g of x equal to negative 1 minus x squared. Okay, so then I know that the area is area between the two graphs. I certainly could write it as a difference of two integrals, as we did before or yesterday. So from negative 1 to 1, 1 minus x squared dx. That's the upper half. Let me mark it. So this is the upper half. And then I subtract integral from negative 1 to 1, negative 1 minus x squared dx. That is the bottom. Okay, and then altogether, they give me the whole thing. Okay, but as you can see, whether we use the formula from last page or we just combine these two together, I apply the sum rule. And what do I get? I combine them into one integral, so I don't have to do it twice, negative 1, 1. And I have twice integral 1 minus x squared dx. Okay, so at this point, I factor 2 out. That's the constant multiple rule, by the way. I have an integral between negative 1 and 1, 1 minus x squared, the integral that we did. Remember, well, how do we integrate this one? The last one?
Trig substitution.
Trig substitution. This is trig substitution. Okay. So we're not going to do it, but we do remember the answer. So it was a big deal to compute the area of the circle, and the answer was pi, right? Sorry, it was pi over 2. So 2 times pi over 2, and then we have pi. The answer, the whole thing is here. The whole circle is computed with a single integration. Okay. So what's left to apply? It is a straightforward formula, no big deal right here. So two graphs are, the origin is held by 4. In fact, I missed this part over AB. So it is held by possibly up to 4 curves, straight lines for A and B on left and right, F on top, G on the bottom. And these 4 might produce a variety of shapes, including circles. But sometimes something more complicated comes up. But let me do one simple example before we do anything more complex. Well, here's one. So this is the way the problem will be stated. Find the area. Sometimes it is very specific. Find the area between y equal x squared and y equal 2x squared plus 1. Okay, between x equal, say, 0 and 1. Okay, so no words are provided for you. Then you have to plot it, figure out what it looks like. Just even though this one is straightforward because both f and g are specified as well as a and b are specified. So that one is straightforward. Sometimes it's more complicated, but this is a, this is b, this is f, and this is g. Hold on a second. The other way around. So if we speak of the area, it is always you got to know which one is larger, so that we are speaking of the area that is always positive, unlike the area under the graph of a function, which becomes negative once it's dipped below the x-axis. This is always assumed to be positive. If I plot the graph, you'll see what I'm talking about. Y equal x squared, it is smaller than y equal x squared. Okay, 0, 1, it reaches 1, let's say 1, okay, and the other one starts at 1 and goes up to, well, higher. Starts at 1 and reaches, well, higher point. Doesn't even matter what it is. So this is what the region we're talking about. Well, so this is the region. You plot it just to confirm that the picture matches the description, rather the picture matches the description in the theorem, in that formula. Okay, so but otherwise a, b, f, and g are identified, so that area is computed as simply the integral of the difference. It really doesn't make any difference. It's a good idea always to remember where it comes from. So it's the region under f minus the region under g. This is f, this is g, and really this area is the difference of two areas. It's just a minor convenience, but just a worthwhile, I suppose. That's the convenience convenience simplification, and so we just we apply the formula. So the area is integral from -1 to, from 0 to 1, 2x squared plus 1 minus x squared dx. So at this time it becomes purely technical. Just remembering the formulas. So integral from 0 to 1, x squared plus 1 dx. Integration is straightforward by the power formula. So x squared plus 1, what's the antiderivative?
2/3 x cubed plus x.
Not 2/3. There's no third. No, it's squared. It's there's no root here. X squared. What's the antiderivative? Power goes up by 1.
X to the third over 3.
X over third over 3 plus x. From 0 to 1, plug in 1 and 0. We'll have 1/3 plus 1 minus 0 minus 0. So it's 4/3. Okay. So that's all there is, really. I just hope you won't forget about where it comes from. Just one more example when there's a little bit of a challenge to when not everything is identified. So sometimes the formula is described, the problem you're going to face. Sometimes the region is described in a way that you might require some work in order to find these 4 missing parts. To apply the formula, you need 4 things, 4 f, g, and a and b, and so some of them might be missing. So this is what I pick. Here it is. So find the area between x equal x squared and, oops, y equal x squared and y equal x cubed. The area of the region in the first quadrant. Okay, so plotting helps in order to identify. As you can see, there is no A and B, so you have to figure out A and B. You have to plot it. So x squared is certainly simple. It is simply the parabola like this. This is 1 and 1. What does x cubed look like in the first quadrant? It starts over here. Where does it continue on?
Does it go up and come back down?
No, it's not. No, it's not going to go below the x-axis. No.
No, but it would come up and like round off.
No. Well, what does x cubed look like? So, but now we need to construct it or visualize it relative to the graph of x squared. So it starts at the same point. Where does it go from here? It goes in roughly the same direction. More specifically. Well, actually, the one way to visualize it to find the intersections. This one intersection of the two graphs is at the origin. Where's another one? 1, 1. Okay, so that's another point. So 0, 0, and 1, 1. So the graph of y equal x squared gets from the first to the second. Is it below or above? It doesn't seem to be crossing it one more time, so they will stay apart, but one is higher, one is lower. Which one is lower or higher? So do I plot it below or above?
X to the third would be lower.
X to the third will be lower because
Of the power.
of the power, yeah, because numbers are less than 1, so they will be growing slower, and then once it crosses, it starts to grow faster than x squared. So generally the idea we know about x cubed that it grows faster than x squared, but only after they part ways at the point 1, 1, right? Okay, up until close to 0, the numbers are so 1/2 squared is 1/4, but 1/2 cubed is 1/8, right? So it's lower, so lower. Of course, you can just plot it with a graphic calculator. So then that is the region we're after. This is the region. It's in the first quadrant. And lower or higher was important. Now we know which one is f and which one is g. So it is actually x squared is f. And x cubed is g. Okay, so you write it out. F of x is equal to x squared. G of x is equal to x cubed. A is equal to 0. B is equal to 1. Right? That's all. So formula, I'm integrating from 0 to 1, x squared minus x cubed dx. Once we compute it, we'll know that if everything was correct, or at least we test, it has got to be positive, and we'll see that it is certainly positive. So power formula again, x cubed over 3 minus x fourth over 4 from 0 to 1, right? Power formula once again. And what I have here is then I substitute 1/3 minus 1/4. That's it. So hold on a second. Okay, yeah. So the answer is 112. Okay? Okay, so there is that's the simplest example of how you use integrals to find things that aren't areas under the graph. So that is the original, not application, not only the original application of the area, the one on the right, but it's also the original interpretation of the integral. It is the area under the graph of one single function. So whenever you encounter something other than area under the graph of one single function, then you have to tweak this idea in order to be able to capture whatever you're looking for. So we did it once with the areas between two curves. Turns out it's fairly straightforward. Both the analysis wasn't too complicated, as well as the formula. Okay. So once again, the idea as why it works out is the additivity of areas, as well as how we actually demonstrated that it works with integrals. Riemann sums is like I said, that idea of dropping a bunch of pencils to the same level. Okay. So the next topic is actually volumes. So we jump from, it's a big jump from areas to volumes. Okay, it is not simple because, well, we sort of have to start over. So I do think that at some point when you discuss Riemann sums, you discuss areas of rectangles. Okay, so you understand areas of rectangles. Area is equal to width times height. That's pretty much enough to start with this to understand all the other areas. So from here you arrive to finding areas of more complex regions. Okay, so that's how it works out with areas. And now we want to do the same with volumes. So then once again we have to start with the simplest. So if we understand the area of a rectangle, now we want to understand the volume of a box. Okay, so but we do, right? So the volume of a box is what? Well, that's right. So volume is let me put in the let's say width, depth, and height. Okay. The thing is that, so we don't want to, however, keep them apart. The idea is, in mathematics, frequently reduce something that you don't understand to something that you do. So we are trying to understand volumes. We want to use what we understand about areas in order to understand volumes. So, do you see areas here in the bottom?
6.
What?
6 surfaces.
No, not what I meant in the formula of the volume.
Width and height.
No. What is the meaning of this?
X and Y.
No. Yeah, okay, kind of, yeah. So what? Width times depth?
It's an area.
It's the area of, that's right, it's the area of the base, right? So that's a big idea, how you can understand volumes in terms of areas. You would just multiply by the height. It is not new. It's not, we already made the one step, that kind of step before, right there, because what is the width? If not the length of the base. Right, so if we understand lengths, then we can understand areas. Okay, that's you just multiply by the height. If we understand lengths and areas, then we can understand volumes in this fashion, because width times depth is the area and the height is still the length. So it's still the length. Length. Okay, so that is a big idea that we're going to utilize in order to understand volumes on a more complex level. But you can see the relation is already there. The relation of how we treat Riemann sums and how we're going to deal with volumes. Riemann sums give you areas. How do we handle volumes? That is the similar thing. So if we understand something that's happening on the ground level, that either the length of the base for the rectangle up there or the area of the base for the box right here, we just multiply it by the height. Okay, so this is the height, and the volume is right here. The area of the base is, that's what I meant. The width times depth gives you the area. So we're not gonna go all the way with this idea, even though it works out perfectly well. It has to be. It will wait until calculus 3. We're gonna make a leap of faith here, and that is this is how what I want to do is. What if the shape of the base is more complex? The idea still applies. So what I'm talking about is, well, how about I'm talking about the cylinder? So what's the volume of the cylinder? Not the formula, but can you utilize this idea? That's right. So it's still the area of the base. So I have this base. Okay, and I will multiply by its height. So area of the base times height. Okay, so it's in all of these cases, I end up with multiplying by the height. Here I had height multiplied by, and this is my height. Okay. The only difference is now my base is curved, and so even though this is plausible, this certainly requires some proof. When we just accept it for on faith that indeed that formula always works. This formula that I have over here always works regardless of the shape, as long as we have something kind of cylindrical. So I could have a very nasty shape at the bottom, okay, and then I build something on top of it like this. Let me try to repeat it. Okay, I sort of, in a way, I lift that base. That is a two-dimensional picture that I made over there on a piece of paper, and then I sort of lift it off the paper, I don't know, 1 inch. And I create, by lifting it, I'm creating a solid object, and now I'm interested in its volume. Okay, so let me make a better picture here slightly, maybe like this. So once again, from a two-dimensional base, we produce a solid, and we know how to find its volume. I still have my height here, okay, and the area is still the red one, area times the red area times the yellow height. Okay, so that is we assume this on faith, even though I hope you see that it is kind of plausible, right? It's plausible. So it's like you take it well. And you just if you go for examples, I suppose you can convince yourself that this is true. So then the point is then what this allows us to do is to compute at least a lot of volumes to begin with, right? So as long as we are able to find areas, that's the progress that we're making, is that this problem has been solved almost, or at least to a large degree. Our ability to find areas is quite high, we can do it with integrals, right? Just those integrals, just regular integrals, definite integrals that we can compute areas of various shapes, including circles or bounded by a sine, by cosine, by parabola, hyperbola, whatever. We can handle those. And so a lot of curves that now can be with this little formula can be now handled. As long as solid is not, we cannot handle, for example, the sphere. This will not help us with the sphere just yet. But at least something that is, if the vertical direction does not produce anything complicated, that's how we can find the area. Just find the area using calculus 1 or calculus 2 as we just did, and just multiply by the height. Okay, so that is not perfect in the sense that then what do we do if we want to do sphere? I want to now. I'm not satisfied. I want a sphere. So, and this you cannot get a sphere this way, right? So if you start with a circle and you lift it, you're going to add a cylinder. You're going to get cylinder, not the sphere. The sphere looks like this, and even though I start, its width, its base will be changing as you're lifting your plane. Okay, so that is the problem. Fortunately, there is a way around it, and that is just assume that we know how to compute areas, and then this is the idea. What do I do with the sphere? This is what I do with the sphere. So I have my sphere. Well, the idea is to cut it into slices. Okay, so what if I slice it up like this? So I cut one slice, and then the next slice. So they're kind of complicated, but only in the sense that they vary in size, but all of these are circles. So these are circles of various radii. But other than that, they're uncomplicated, especially if we assume, now that's the crucial step that we already have done. So we assume that they are approximately straight. What I mean by that is that they're cylinders. So if you slice your, so suppose you have a piece of cheese, but not in the form of a rectangle, maybe it's kind of circular. If you cut it in entirely very thin slices, then you look at the edge and it looks like this. It doesn't look curved, it looks straight. So that is the idea, which is not entirely new, comes from calculus 1 and Riemann sums, and then we'll just add these together. So add them. When you add them, you end up with a Riemann sum, and then we know how to handle that later. So we'll just finish it next time.